So welcome everyone. So it's my pleasure to welcome Molei Tao. We'll be talking about machine learning means dynamics, manifold optimization with momentum, and the implicit biases of large learning rates and learning mechanical dynamics. Yeah, thank you.
Thank you so much for the introduction, and then also spending the effort in describing the whole long title. It's my real pleasure to be here and present our work. And I really thank Boumediene for his kind invitation. So like many of the experts here, I'm a believer that dynamics can actually play an important role in an interaction with machine learning, just like statistics and probability. And therefore, I'm gonna actually share with you some of the efforts, some of the directions that our group is developing in. And hopefully that this can draw the interest of people or create more discussions. I'll be mainly talking about three things. Number one is that we believe dynamics can actually help design and analyze optimization, sampling, and deep learning algorithms. And for that purpose, I'll give one example where we will actually design accelerated algorithms for doing optimization in nonlinear, in certain non-Euclidean spaces. And the second thread is that we think that dynamics can help us gain quantitative understanding of deep learning practices. And for that purpose, I'll talk about some of the non-trivial implicit biases, implicit regularization effects of large learning rate in gradient descent algorithm. And roughly speaking, large learning rate can actually give you better test accuracy. And lastly, I'll talk about machine learning for dynamics. I'll talk about how machine learning can basically feedback and benefit dynamics as well. And this is, of course, under the umbrella of machine learning for sciences and scientific computing. And the example that I'll give is that I'll actually learn structured dynamics from data. And this structure is very important. And by gaining this structure, we can actually get very long time accuracy of prediction. So I can actually predict a very long time with provable good accuracy. Before I start describing the details, I first of all do want to apologize. I lost my voice because of flu. So if any of the things that I'm saying is not clear, please feel free to interrupt at any time. And also, Boumediene kindly offered that I can actually go beyond 1 hour, but if that's, well, so I anticipate the whole talk to take about 70 minutes. So if that's too much over time, I do apologize, but hopefully you will find some parts of the talk entertaining. So that's my goal. Okay, so without further ado, let me first talk about accelerated optimization. So let me start with a smooth unconstrained optimization problem in vector space. So I'm just trying to minimize this function, and gradient descent is a very popular method used in machine learning for this task. And what is funny is that when practitioners talk about gradient descent, sometimes they actually mean gradient descent with momentum, which is a family of popular methods. And they do so usually for a reason, because gradient descent with momentum oftentimes give you faster convergence. And in fact, one member of this family is called Nesterov accelerated gradient for convex functions, or NAGC for short. And it uses this update, and you can clearly see that different from gradient descent, it actually introduces an auxiliary variable y. And this y is basically helping you to memorize the past gradient values along the iteration, and therefore giving you better convergence, giving you a better grasp of the energy landscape in some sense. More precisely, if you have a convex F, you can prove very easily that gradient descent converges like 1 over k, where k is the number of iterations. Whereas for NAGC, the convergence rate actually gets accelerated to 1/k squared. So this is why people said, oftentimes called this an acceleration due to momentum. But of course, the question is, what exactly is momentum? So there are a lot of explanations. I had a background of physics to some extent, so I like the following explanation. So if we view the small h limit of gradient descent, of course, that's just the gradient flow. So gradient descent is a forward Euler discretization of the gradient flow dynamics. And you can do the same thing to gradient to NAGC. And in fact, you can let this time step, this analog of time step eta go to 0. And then in a beautiful paper by Su, Boyd, and Candace, they showed that in this limit, you are actually dealing with a damped mechanical system. And this P is naturally the momentum of the mechanical system. And if you track everything, you will see this P is actually a rescaling of the difference between adjacent Y values. Okay, so that's why, you know, this Y, or more precisely, the difference between Y values is really playing the role of a momentum. So all these were done, classical theory, very beautiful. And what I'm trying to think about is the case where you don't really have a function defined in Euclidean space, but on a manifold, or even some special manifold such as Lie group. And what can happen? If you think about it, of course, the vanilla version, the original version won't work because this gradient is possibly in the tangent space, depending on how you define it. But even you make it to be in the tangent space, this x is in the base, and you take a linear combination, that thing has no geometric meaning. So you have to do something else. And in fact, you know, how to do gradient descent on manifold is a deep field developed by well developed by many experts. What I'm trying to do here is I want to have a momentum version, a manifold or Lie group. And if you think about this, this is only harder because then you have to deal with second order derivative. And if you cannot really deal with the first order derivative well, you know, second order derivative could only be harder. So so the roadmap of my my strategy is that I'll actually first construct continuous dynamics that actually does the optimization, and then I'll discretize this dynamics very, very carefully. By discretize, I mean discretize the time. So I'll get you know, an algorithm, and the algorithm will actually stay exactly on the manifold, and it does the optimization. So that's the plan, and this part of the talk is based on this work. It has a very long title, but I'll explain what we did. It's published in AI Stats, which is a machine learning conference, so you can actually find it online. It's a joint work with Tomoki Osawa from UT Dallas. And basically, the approach that we use is a variational approach, and we do that for two reasons. Number one, it generalizes well to non-Euclidean spaces because somehow this approach is actually intrinsic. Secondly, it naturally introduces momentum. Of course, you know, everything has an origin from mechanics. And when we talk about mechanics, we cannot avoid Newton. So Newton said the rate of change in momentum is given by the force. And you can easily translate this into mathematical language. You get a system of equations. And P is the momentum. But then Lagrange came along and said, you can consider an equivalent problem. Okay, you can construct a variational principle. Or more precisely, you can first define an action function node. So this S is a function of path. So it's a function of function. And if you define it as the integral of a quantity called Lagrangian along time, and use a Lagrangian given by this. So it's kinetic energy minus potential energy, and you use this the F here as your potential energy, and then And then if you look at the Euler-Lagrange equation associated with this, this action, then you get exactly Newton's equation. So these two are completely equivalent. And you might wonder, so why is this relevant to optimization? Well, so far I said no, I mentioned no relevance. And if you think about it, the reason is because, okay, so this Lagrangian is actually not explicitly dependent on time. So if you know mechanics, this is a symmetry. This is a time invariance symmetry, time translation symmetry, and as a consequence, you have a conservation law. But in plain language, it's just you have conservation of total energy. Kinetic energy plus momentum, plus potential energy is independent of time. So what happens if you follow this dynamics is that the value of F is just fluctuating because the potential energy is constantly exchanging with the kinetic energy. Okay, and but that's really because you have this time translation invariance. In fact, if you break this time translation invariance, if you make L to be time dependent, then the story changes. And in fact, in a beautiful paper by Vibisono, Wilson, and Jordan, they constructed an explicit time dependence by multiplying the original Lagrangian by some explicitly given time-dependent scalar factor. And then you can actually prove very easily that the corresponding Euler-Lagrange equation has an additional term, which is this frictional term. And the coefficient gamma is actually determined by this R. And of course, this is a damped mechanical system. You can rewrite it in the form that we just saw. And it's very easy to prove by a simple argument, simple energy argument, that the value of the Q function as t goes to infinity will converge to a local minimizer of the potential energy. So this is why this dynamics is doing minimization. And in fact, if you choose R such that gamma becomes 3 over T, then you have some dynamics, and one discretization of the time of this dynamics gives you the popular method that I just showed you, namely an AGC. And there are other variants. For example, if you make gamma to be a constant, some discretization gives you an AGSC, which is Nesterov accelerated gradient for strongly convex functions, and some other discretization gives you heavy ball. As a contrast, we can also look back at gradient flow, and one discretization of gradient flow actually gives you a gradient descent without momentum. Okay, so why am I doing all these? The reason is because, like I said, actually, let me go back. So if you stare at this dynamics, this system of ODEs, and you try to extend it to manifold, it's not easy, because suppose Q is on the manifold, then what is P? You may think that P is in the tangent, but in fact, if you are a geometric mechanics person, P is actually in the cotangent. But what about P dot? What about the stuff on the right-hand side? So things can actually become very messy. And that's why a lot of really smart people had various ways to deal with acceleration with momentum on manifold. But now, if you start with variational principle, you have a very elegant way of generalization to manifold and Lie groups. So let me first take a moment to explain what I mean by a Lie group. So I think for most of you, this should be trivial, but just in case. So a Lie group is a group that is also a smooth manifold. A very popular example is a special orthogonal group. And it basically consists of matrices that are orthogonal and assuming a positive signature, well, a positive determinant. And why do I want to minimize over, for example, this group? Well, for instance, let's think about matrix diagonalization. So you are basically looking for a member of this group such that you use via a similarity transformation, it turns a given matrix into a diagonal form, and therefore placing zeros off diagonals. So you can actually minimize, the sum of the off diagonal elements, or more precisely, the sum of the magnitudes of them. So hopefully that gives you some motivation about why you want to do optimization on manifold, such as Lie groups. And we want to solve this problem, again, using gradient-based approaches. But then, of course, you may ask, what do you mean by a gradient? And in fact, this is a non-trivial question, and here is why. So let's consider a known example, just SO2. So rotation actually in 2 dimensions, and consider a special objective function, which is just the determinant of the matrix. And then a careless person may say, oh, but then everything's easy because you can compute the determinant, and then you just collect all the partial derivatives, and then that's your gradient. But that's actually false. If you think about it, special orthogonal matrices always have a determinant of 1. So f is 1 everywhere on the manifold. So the gradient should actually be 0. So why is the discrepancy? Well, the reason is because SO2 is actually a 1-dimensional manifold. It's not 4 dimensions. Because you have a constraint. Okay, so this is a constraint. And therefore, all the 4 components, A, B, C, and D, they are actually dependent on each other. So you cannot just brute forcefully collect partial derivatives and then form some gradient. Of course, that's just the tip of the iceberg. Like I said, manifold optimization is a profound and extremely active field. But I will just focus on adding momentum. And the variational principle, like I said, is a good way to do it. And like I said, in Euclidean space, you can consider this time discounted Lagrangian and look at this variational principle, and then you can actually get optimization dynamics. If you had, on the other hand, a Riemannian manifold, and then you stare at this Lagrangian for a while, and then you realize the only part that is that is creating trouble is this part, is this kinetic energy part. But if you had a Riemannian manifold, and G is basically a path, a time parameterized path on this manifold. So it's traveling, for example, along this ball, the surface, this sphere. And then G dot is actually in the tangent space. And you can actually use the Riemannian metric to define an inner product. And then everything else actually remains the same. What is even more interesting is if you actually have a Lie group. So this Riemannian manifold is actually a Lie group. And then you can do something more. You can do something very natural. What do I mean by that? Okay, so G dot is actually in the tangent based at G at time t. But what you can do is you can actually pull this entire tangent space back to the tangent space at the identity element of the group. So this tangent space is known as the Lie algebra. So this is what I meant by that. And what you need to do, for example, to pull this G dot back to the Lie algebra is you simply, for example, do a left inverse multiplication, left multiplication by the inverse of G. And then you get a very special tangent vector. And you also need some metric or an inner product. But one thing you can do is you can use something called a natural pairing between the cotangent space and the tangent space. So you need an isomorphism from the tangent vector, from the tangent space to the cotangent space, and then you can just use the natural pairing. So honestly, if you, I think I'm being too fast. So if you haven't seen things like this before, you will think that I didn't explain well. And in that case, I apologize. But what I'm trying to say is that, okay, so if you use this intrinsic thing, this intrinsic formulation, you can actually derive the corresponding Euler-Lagrange equation for the variational principle, and you actually get a system of ODEs. Okay, so G is again the variable you want to optimize. It changes according to something like velocity. So Kc is no longer just the velocity, it has to be multiplied by G. And then Kc actually changes by the second equation. So in fact, this isomorphism sort of maps the velocity, or if you prefer, angular velocity to angular momentum. So the left-hand side is really a change of momentum. And the right-hand side is interesting. It has three terms. The first term is actually the dissipation term, the frictional term that we saw earlier. This is critical for optimization. The third term is sort of like the forcing. And the second term, so the first term has this coefficient gamma, which is actually given by R. You can make it to be constant or 3/T or something else. And then you have a second term, a new second term, which sort of accounts for the nonlinear geometry and the corresponding force. Okay, so everything sounds very abstract, but in fact, it can be made very concrete. And here is an example. So suppose I just want to compute the largest L eigenvalues of a given matrix A. Of course, you can formulate this as a minimization problem. You just change the sign of A, so no big deal. And you can formulate an optimization problem by defining a function on the orthogonal, special orthogonal group. So basically, you use this R to diagonalize this matrix A. And then you use the constant matrix E to only keep the top left L by L block of the resulting matrix, and then you're trying to minimize the trace, and you can actually convince yourself that effectively this is helping you to find the smallest L eigenspaces. And if you use this objective function and plug that into the equation, the general equation that I showed earlier, you will get a system of ODEs like this. And R and Kc are just n by n matrices here. And this square bracket is the common matrix commutator. And I don't have to worry about geometry anymore. In fact, here I just have everything working in the ambient Euclidean space. And if your initial condition is consistent, meaning that, okay, initially R is special orthogonal and Kc is in the tangent, which you can show to be corresponding to skew symmetric matrices. And then you evolve this dynamics. No matter how long you evolve, you preserve those geometries. So R will remain to be special orthogonal and Kc will remain to be skew symmetric. And moreover, this R will actually converge to a local minimizer of the objective function. Okay, so that's the continuous picture. But of course, you may wonder, that's not enough, right? So we need an algorithm. So from now on, I'll actually discretize the time of this dynamics. And for simplicity, I'll use a constant time step, but it doesn't have to be so. And my goal of this discretization is number one, I still want to have an algorithm that optimizes, and also at the same time, equally important is I want to make sure that my R and Kc still stay on this geometric structure. And I can actually do that. So the way we do it is we use an operator splitting idea. So we view the vector field associated with this dynamics as the sum of two vector fields, and I evolve each one of the vector fields respectively. So the first one has a 0 for the R component, and the second one has a 0 for the Kc component. if you look at the first dynamics, it's very good because it's explicit and you can exactly solve it, and the solution expression is explicit. The reason is because yes, you have nonlinearity here, which I actually abstracted as a function g, because because this approach works for other cost functions. So you don't have to really deal with this specific form. And in general, you will have this nonlinear function g. But even though it's very nonlinear, r is going to be a constant. So effectively, you are solving a linear dynamics here. So everything is explicit. And for the second part of the equation, sorry, for the other dynamics, you have the same thing. The solution is exactly and explicitly available because R just evolves according to a linear dynamics. So for the computational mathematicians, you may worry that if Cassini is very high dimensional, then taking the exponential of this Cassini matrix is computationally expensive. But there is something called Cayley transform that actually can do this very cheap way without affecting any of the structures. And once I have the solution flows of these two dynamics, I basically do, for instance, H time flow of B, and then I do H time flow of A. I don't know why this red box gets misaligned, but basically, if you do H step of B and then H step of A, then you get one H step, one approximation of the H time flow of the original system. So this is guaranteed by operator splitting theorems, actually. And then, of course, you iterate. You keep on iterating more and more steps, and then you can get a good numerical integrator. In fact, this is a very good numerical integrator because number one, it's going to be exactly on the Lie group. For example, so if you take a look at the flow by A, of course, it's exactly on the Lie group because R doesn't change. So it stays on the group. Cassini changes according to a linear dynamics. And you can easily prove that if it started being skew symmetric, it remains to be skew symmetric because the evolution is given by a scalar. And this thing is actually a skew symmetric matrix as well. And same thing for B, because C doesn't change, so it actually stays on the dual of the Lie algebra. Sorry, it stays on the Lie algebra, and R actually changes according to the exponential of Cassini, which by definition stays on the manifold. And there's something else that is very nice about this numerical integrator called conformal symplecticity. It's a little technical, but roughly speaking, the original dynamics actually shrinks phase space volume in a specific way, dictated by gamma. And the discrete dynamics, the discrete in time dynamics actually does exactly the same amount of shrinkage of phase space volume. So this is why it's doing optimization in a faithful way. You can make the numerical method to be arbitrarily high order. What I just showed is a first order method, but arbitrary high order operator splitting schemes exist and in fact is popular. So that's not a problem. And the convergence property is very nice. So usually in numerical linear algebra, if you want to get the top eigenvalues, or actually all the eigenvalues, or just the first eigenvalue, you will rely on the spectral property of A. For example, how large is the largest eigenvalue when compared to the smallest one? This is known as spectral gap. And condition number also comes into play very often. And the convergence of this algorithm is independent of these things, at least not directly. The reason is because if you add any constant diagonal matrix to A, you shift all the spectrum, but it doesn't change this dynamics. This constant will just drop out after you take this matrix commutator. So you have very robust convergence. And in machine learning, people oftentimes also have to deal with stochastic gradients. And in this case, you basically have to deal with something called an online problem, in which you may not have full measurement of A. You may only have partial measurements of A or noisy measurements of A. And then a lot of the traditional numerical linear algebra problems, algorithms will no longer work, because maybe you try really hard to construct subspaces of A increasingly, but then A gets changed, and then all the previous work actually gets messed up. But if you use this dynamics-based approach, you actually can prove a good generalization to cases where A becomes stochastic. So so that's another advantage of this approach. Okay, so enough talking. Let me show you some example. Oh, is there a question? Yeah, so the question is why SON helps achieve these advantages. It's not really SON that achieves those advantages. It's the carefully constructed dynamics in continuous time that does the optimization, and also the careful discretization that helps the discrete algorithm to stay on the manifold and abiding all those good properties of the continuous dynamics that altogether contribute to these advantages. So hopefully that answers the question, but let me know if I am wrong. Any other comments, questions? Okay, so here's one example. So here I arbitrarily generated a 500-dimensional matrix, and I just want to compute the largest, the two eigenvalues. So roughly speaking, red and yellow are results of the new approach. X-axis is the number of iterations. Y-axis is how far away you are from the maximum value of the objective function. So you can see significant acceleration when compared to SOTA methods on the market. That's a toy example, but here is a real example. So I'm actually using MNIST data set. I'm performing some statistical task called LDA, linear discriminant analysis, which basically corresponds to a generalized eigenvalue problem. And for the sake of time, I will not say too much about the setup. But again, red, which is our approach, is the best. Yellow is the other version of our approach. So yellow uses basically the dissipation coefficient of 3/t. Red uses a constant. So yellow in this case is not the second best. This blue is actually doing pretty well as well. And this blue is actually the correct way of doing gradient descent on the Lie group. And the reason is that here, this problem is probably corresponding to a strongly convex problem. So if you know the details, the yellow approach, which is for convex problem but not strongly convex problems, naturally has a disadvantage. But I think that's enough details for part one. So let me summarize. So we constructed a variational principle from which we were able to derive ODEs that evolve on Lie group that does optimization in continuous time in a nested of accelerated gradient fashion. And then we have to discretize these dynamics very, very carefully. And then we get structure preserving integrators, which are basically our optimization algorithms, which operate in discrete time. And those algorithms actually correspond to a very natural way of doing gradient descent with momentum for Lie groups. Of course, for the whole thing to flow, we were thinking that those integrators are discretizations of the ODE. So you may think that the time step h has to be small, But in fact, in practice, you can use relatively large time step as well. And in fact, this is going to be the focus of my second part of the talk. So I want to understand what happens to gradient descent if your learning rate, if your time step is big. Of course, one easy thing to say is that you will get efficient computation if you still have convergence. That's because if you want to simulate to a fixed time, call the time t. The bigger h is, the smaller t over h would be. So you would spend less steps. But in fact, you can get things beyond that. And very roughly speaking, I'll try to show that if you use larger h, you can actually get better test accuracy in a machine learning context. This is actually pretty non-trivial, so I will no longer bother with the curved geometry. I'll just work with gradient descent in vector spaces, Euclidean spaces. So that's part 2. And because we are now trying to understand some aspects of deep learning, let me first do a quick overview, a quick review of some of the jargons and terminologies that I'll be using. So a paradigm of supervised machine learning has a training phase. So here you have given training data, which is a collection of pairs. Each pair has an input domain, input component, and also an output label. And the goal of supervised learning is that you pick a model called G. It's a parameterized model, and you want to find the parameter of this model. For example, the weights and biases of a neural network, such that if you use this model to predict the label, you get good matches with the true label. So clearly, this is a minimization problem. And the thing is, oftentimes, G is going to be complicated. For example, if G is a neural network, this F is going to be a highly non-convex function. So if you're unlucky, you can actually get trapped in a local minimizer of F. And in fact, this happens very often if you're not careful. And that's actually bad, because that means that you are actually achieving suboptimal training accuracy. So there are actually better X values that can make the match better, but you cannot find it because of the limitations of the optimization algorithm. What I'm trying to say is that if you use a large learning rate in gradient descent, then you can actually escape from local minimum. And that's going to be what I'll talk about in part 2a. There's also a testing phase. So suppose you have found your parameter after training, and you are given new data, and you want to see how good is the prediction given by this model. And if you think about this, this is actually a different problem. For instance, suppose this F, suppose you've already found the global minimizer of this F, but maybe this F actually has multiple global minimizers. And if that's the case, then what you use here as a parameter matters a lot, because different global minimizers can actually give you different test accuracies. So the discrepancy between test accuracy and training accuracy is sometimes called the generalization. And generalization is what matters a lot in deep learning. So in part 2b, I will argue that if you use a large H in gradient descent, you can actually favor minimizers that generalize this well. And I'll be more precise as we reach that point. But let me first talk about part 2a, which is about large learning rate creating a mechanism of escape from local minimizer. This is based on a paper published in Europe's machine learning conference about 2 years ago, and it's joint work with my PhD student Lin Kai Kong. So the setup is very simple, gradient descent. But if you think about it, large H actually is not completely trivial. Let me explain. So if H is very small, then you would just have monotonic convergence to a local minimizer of, for example, this simple potential landscape. So that's a monotonic convergence. If you make H to be bigger, you can still have convergence, but you may actually lose monotonicity. So you can have this oscillatory behavior. If you make H to be even bigger, you can actually have instability. So you are actually not convergent at all. So that's easy. But what if this potential landscape is just a microscopic part of a macroscopic potential? So so then you have this multi-scale landscape, and I do gradient descent again with a large time step, and you can track the x value by tracking this red dot. And in fact, at least I cannot really track it, because it's very hard for me to predict where it'll go in the next step. And in fact, here I plotted the trajectory of x as a function of the number of iterations. So this is just a single trajectory. And you see this very stochastic-like behavior. And in fact, I collected the values that x takes along this single trajectory. I plot the histogram of these values, and I almost see a rather good statistical distribution. So it seems that the deterministic dynamics of gradient descent. So remember, I'm using completely deterministic dynamics, but it nevertheless exhibits behavior that looks like stochasticity. And in fact, I think most of you are familiar with SGD, and this stochastic behavior is almost the same as that of SGD. So what's going on? So we do have a theory. The theory is rather precise. It's saying, okay, so if your objective function is multi-scale and you use a large learning rate, and then the deterministic dynamics of gradient descent actually is chaotic. And that's why you see stochastic-like behavior. So let me explain what I mean by a multi-scale objective function. So I require my objective function to be the sum of a macroscopic potential, which, for example, could look like this, plus microscopic potential that is indexed by a small parameter epsilon. And one example of a microscopic potential is that you take any periodic function f1, you squeeze it in the x direction, you squeeze it in the y direction, and then you get your micro potential, and you add it to the top of f naught, and then you get a multi-scale landscape. Of course, mathematicians like microstructures like this, but practitioners don't, because this is too artificial. But the microstructure doesn't have to be periodic. Here is another example of quasi-periodic microstructure. Now you see much more natural small-scale behaviors, but we don't require this either. So our requirements are a little technical, but it's actually very mild. So roughly speaking, I require the micro potential to have a gradient that is convergent to an order 1 random variable. And in addition, I also had an assumption on the second order derivative. It needs to be order 1 over epsilon, which makes sense, because if you differentiate twice here, for instance, you get 1 over epsilon, and similarly here as well. So that's what I meant by multi-scale objective. What about a large learning rate? So let me first explain what I mean by a small learning rate. So in fact, in optimization, it's well known that if the learning rate eta is smaller than 1 over L, where L is the Lipschitz constant of the gradient of the whole thing, then you would just converge to a nearby local minimum. In this case, this gives me a requirement that eta has to be smaller than epsilon. In this case, the dynamics completely resolves the small scale of the potential, and you just get boring convergence to a nearby local minimum. What would be a bad learning rate, on the other hand? Well, so if eta is arbitrarily large, then you cannot even resolve the scale given by f naught, even if you discard f1 epsilon, so you no longer have a source of stiffness, you still cannot resolve this, and your iteration can actually be unstable. So this is, of course, a meaningless end of the spectrum. But in between these two ends of the spectrum, you actually have a lot of spaces. And in fact, this is the interesting case. This is where I call the learning rate large. And I will show that as eta increases, you will first enter a regime called that I call local chaotic regime. And as eta further increases, you will enter something else that I call global chaos. Let me first explain local chaos. Excuse me. So if you view gradient descent as a deterministic dynamical system, we can look at the attractor of the dynamical system. So when eta is very small, in a neighborhood of a minimizer of the objective function, this minimizer is actually a fixed point, and it's actually the only attractor in this neighborhood. But as eta keeps on increasing, you will encounter a bifurcation. So this fixed point will still be a stable fixed point, but it's no longer stable. And instead, nearby, a periodic orbit of period 2 will actually emerge, and that actually corresponds to a stable attractor of the system. And as eta further increases, the period actually keeps on doubling, and the system quickly transitions into chaos when the period actually becomes formally infinity. So, so at this moment, X actually stays within a microscopic potential well. So, so this potential well is created by F1 epsilon, and it's of width epsilon of depth epsilon. And in this case, there's a tool called unimodel map that that helps well understand what's going on, this chaotic dynamics. But that's not it. So if you further increase eta, as you can see, the boundary of this chaotic attractor actually keeps on expanding, and the dashed lines are actually the boundaries of this potential well. So you can see that it seems that when eta becomes large enough, you will get out of this boundary, and that's indeed the case. This is easy to understand because, okay, so if you are here, your gradient is pointing to the right. If eta is large enough, then of course your update will get out of the local minimum, local potential well. So that's actually when the dynamics enters global chaos. So in this case, we have very interesting results. For example, so if the macroscopic part of the potential is strongly convex, C2 and L smooth, then the limiting distribution of phi actually is not direct. So it's no longer convergent to a point. It's actually convergent to Boltzmann-Gibbs distribution given by this. The proof is actually technical, so I will skip that. But I'd rather talk about the implication of this result. So the actual loss function may look like this. Okay, so it's multi-scale. You have a lot of local minima because this microstructure creates those small scale local minima. But what appears in the limiting distribution is dependent only on F naught. Okay, so that's F naught, and the corresponding distribution is the one given by red. Okay, so so therefore, because gradient descent is going to be sampling approximately from this red distribution, it's not even seeing the F1s. So it's not seeing those local minima. And that's a quantitative mechanism of escape from local minimum. It's a pure effect of large learning rate. It's very different from the commonly understood escape mechanism, which is via noise of the gradient. Here there's no noise. People may wonder what happens if F naught, the large scale potential, is non-convex as well. We also have theories, but for the sake of time, I'll skip that. But rather, there's an equally important question, which is, okay, so multi-scale potential is nice, but do we really have them in practice? Do we have real problems that correspond to multi-scale potential? And the answer is yes. So here we actually did some empirical experiments. We trained a small neural network on a real data set, and the task is regression, and we train it by gradient descent with large learning rate. So maybe it's easier to look at this plot. So this is the value of one parameter of the model as a function of the number of iterations. You see, it actually doesn't converge to a point. It converges to this blob. And this blob is actually the marginal of the invariant distribution. And likewise, here I'm plotting the histograms of, for example, the loss of certain parameters in the model. You don't see a direct distribution, which is what you would see if you have convergence to a point. Rather, you actually see some complicated non-convex distributions. So you can actually converge to a distribution. And we actually had partial theory. And the idea is the following. So, you have multi-scale loss, maybe because you have multi-scale training data. And oftentimes you have multi-scale training data because the data is usually corresponding to fluctuations about a mean. And then maybe the loss actually inherits this multi-scale structure. But this is actually not trivial because the loss is a function of the parameters of the model, of the neural network. It's not a function of the data. The data is already given to you. So somehow there's a duality, and we can actually show this duality in a very specific context where you actually have just the two layers and you use periodic activation. And then the loss actually inherits a multi-scale structure. So as a summary, deterministic gradient descent can actually escape local minima if the local minimum are actually microscopic and the learning rate is large. And that's because the dynamics is chaotic. And then gradient descent no longer optimizes. It actually samples from a statistical distribution. I see there's a question. So yeah, okay, so this is a technical question, but a very good one. So yes, so if you have mini batch, then your gradient is going to be stochastic. So you will have actually two effects. One is from the stochasticity, from the variance of the gradient, and the other is from the large learning rate. And these two effects can actually add up. Of course, now if your mini batch is dynamically adjusted, that's also very interesting. We also had some work, but then you know the stochasticity is more complicated. It can be dealt with, but it's a little beyond what I can talk about right now. But thanks very much for the question. Yeah. Okay. So why this matters? What I just said matters? The reason is because it basically says that okay, you have higher probability of getting into deeper minimum. And of course, deeper minimum gives you better training accuracy and oftentimes better test accuracy. So that's good. What I'm going to do next is I'll say that with large learning rate, you can actually get to flatter minimum as well. There is a common belief that flatter minimum gives you better generalization. This belief is never proved, and I'm not going to prove it either. And in fact, I know there are a lot of evidence, but I also know there are compelling results that show the contrary as well, that disprove this as well. So I'm not going to say anything about generalization correlation with flatterness, but I'll actually show that if you use a large learning rate, you can actually get to flatter minimum. And this is joint work with student Yuqing Wang and student collaborator Mingshuo Chen, his advisor Tuo Zhao, and the paper was recently accepted by another machine learning conference, iClear. The problem that we studied is called homogeneous model. Let me explain a little bit what I mean by homogeneous model. So a two-layer neural network with ReLU activation is a homogeneous model. You can easily define its objective function. It's a function of two matrices. Sigma here is the activation function. If we consider ReLU, it's a very nonlinear function, but it actually enjoys a nice property known as homogeneity, meaning that if you scale the input by a constant, the output gets scaled by the same constant. And because of that, you actually has a nice structure. So if you multiply W1 by a scalar and divide W2 by the same scalar, then you get the same value of the loss function. So this is actually a symmetry, and this symmetry has a lot of profound consequences. For example, you have a set of continuous minimizers. Because you give me a minimizer, I take a C close to 1, and then I can find the arbitrarily nearby minimizer. But among those minimizers, some actually generalize better than the others. And like I said, let's assume that maybe the flatter minimizers generalize well. And the question is, what will we get after training? If we train by optimizing this function using gradient descent, will we actually get those flatter minimizers? I think this is a question to the heart of deep learning, but of course people may ask, what do you mean by deep learning if you're just dealing with two layers? Well, so first of all, this homogeneity and this symmetry is not restricted to two layers. My presentation will be. And in fact, in deep learning, people sometimes even consider two-layer linear neural network. And even this problem has a lot of things that are still not known. So it's still meaningful. And it's actually also closely related to a problem in data science known as matrix low-rank factorization. So there you are given an n by n matrix A, and you want to find a rank D approximation of this matrix. And one way to solve this problem is to look for n by D matrix X and Y, such that you use X and Y to approximate A. So you basically minimize the discrepancy, the approximation error. And in fact, these two problems, the last two problems are almost the same. They are both easier than two-layer neural network. And I will actually focus on matrix factorization in this talk. So people like to study matrix factorization because, well, partially because every local minimum of this objective function is a global minimum. If you know stuff like NTK mean fields, you know there are also connections, but that's beyond what I can do in my time. And among those global minimizers, some of them have balanced the norms, some of them don't. And the balance actually matters because you can easily prove that the ones with balances are actually the flatter ones. They have flatter local geometry. And unbalanced X and Y's actually give people a lot of trouble. So if you think about it, for example, if you write down the gradient descent iteration for this objective function, you actually have nonlinearities here and here. So if X is small, Y is big, then this term is very big, but this term is very small. So in order to accommodate this big term, you have to pick H to be very small, but then Y barely changes. So numerically, you have a lot of issue. And in fact, this is a consequence of a lack of global Lipschitzness. So analysis will encounter issues as well. And that's why a lot of people actually add regularizations to this objective function. So they create an extra artificial balance, encourage a balance between X and Y. But in an interesting paper in 2018 by Du, Hu, and Li, people showed that in the H going to 0 limit, the initial extent of norm balancing is actually maintained. So you just have to pick well-balanced initial conditions, and then you don't have to worry about unbalancedness which plague analysis and simulation. What we do here is the contrary. We show that if you use a large H, then you can actually get balance, even if initially you're not balanced. And the larger H is, the more eventual balance you will get. And in fact, it's even beyond a balance of norms. It's element balance, element-wise balance. So you have some error bound like this. So bigger H, of course, gives you a smaller discrepancy between these two. And this is independent of initial condition. So I think I'll skip some of those details and just to show you the results. So so here is one example. I'm given some matrix A and look, and I try to find a factorization of this matrix A. So if I use the learning rate that is too large, I'll just get instability. So X and Y will just blow up along my iteration. But if I use an H that is very large, much larger than the Lipschitz 1 over the Lipschitz constant, I actually will get relatively good balance between the norms. If H becomes smaller and smaller, the balance actually becomes worse and worse. Okay, so so this actually gives you, well, I'll skip the proof as well. This gives you basically implicit biases. Okay, so large learning rates are actually implicitly biases towards balanced local or global minima in this case, and balancedness actually gives you flat global local geometry around the minimum, and therefore large learning rate actually favors flatter global minimum. And of course, this is only for the problem of matrix factorization. It generalizes to homogeneous problems. But if you want to know more details, I'll be happy to talk about it. Finally, I want to very quickly talk about machine learning for dynamics, and in particular, I'll talk about learning dynamics and prediction. So this is a joint work with my former student Ren Chen, and it studies a problem of interest to many, which is that, okay, so given time series, can we learn the underlying dynamics that generate this time series, and can we make predictions? Can we actually predict far ahead in future of the evolution of the time series? And the particular context that we will be considering is where the time series are generated actually by mechanical systems. And in this case, you have a structure, which is the structure of mechanical systems. And because of this structure, we can actually get very long time prediction accuracy. So why do we want to predict the mechanical systems or learn the data generated by mechanical systems? Well, that's because our world is mechanical. So here is one example of a planet precessing around a star. And this is a mechanical system. And even though the trajectory is completely continuous, in reality, what people can observe are just discrete dots, maybe the red dots in discrete time. And what we want to do is to predict the green dots, the future evolution. So you see, this is a very long time future evolution that we want to predict. And that sounds like mission impossible. But in fact, we have to realize that this is a mechanical system. So we have additional constraints and structures. Typical structures that people tend to think about include, for example, conservation of energy and conservation of momentum map, or if you prefer a planar language, linear momentum, angular momentum, etc. But if one digs further, there is actually an underlying geometric quantity known as symplecticity that is actually preserved by the dynamics. And the preservation of symplecticity sort of gives rises actually to those conservation laws. So therefore, what we do is we actually hardwire this preservation of symplecticity in my learning model. And consequently, we can provably show that it gives us superior prediction accuracy over long-time prediction. So let me be a little more precise. So I'm given a training data that consists of multiple time series. So I is basically the index of my discrete time. J indicates which sequence that I have. And our perspective, our approach is we assume there is a latent dynamics generated by this evolution map phi that evolves things forward in time. And we want to learn this evolution map phi. Once we learn it, the prediction or forecast is trivial. You just iterate this map phi. That sounds very natural, but in fact, this is a little different from traditional approaches based on differential equations. So it's very popular to assume that there is a latent dynamics governed by some differential equation, and then it generates a continuous trajectory and the observations. The time series are just the observations at discrete time of that continuous trajectory. And then this differential equation approach tries to learn this vector field F. But F is not the same as phi. Okay, so F is sort of like in the tangent and phi directly makes the jump. And if you think about it, there are several sources of inaccuracy if you use differential equation. So number one, you're only given discrete in time data, so you have to approximate the time derivative. And then you have to find F that matches the time derivative. So you have function approximation error. And lastly, you have to integrate what you have learned. So this ODE is something you have to integrate if you want to make future predictions. And then you have numerical integration error. For the map-based approach, you only have function approximation error. In addition, you can actually hardwire physics into this approximation, into the model. And the physics that I was referring to is, in this case, symplecticity, which is basically requiring this map phi to have a Jacobian satisfying some nonlinear equation. And you may think this to be something out of nowhere. But in fact, if the latent dynamics is Hamiltonian, then it's guaranteed that the true phi is going to be symplectic, satisfying this condition. So therefore, I want to actually enforce this condition exactly. I don't want to have any approximation. So I don't want to have a problem, an objective function that has this as a regularizer. I want to enforce it exactly so that my model is mechanical. So that's going to be a hard constraint. So the goal is to find phi that satisfies this and generates my time series. In order to do that, we use a little bit of math. We indirectly represent this symplectic map phi by something called generating function. So if you're not familiar with this, there's a very deep Hamilton-Jacobi theory behind, which I cannot cover. So let me just trust me that given a generating function, which is a function of two variables, there is a corresponding phi, which is also a function of two variables. And this corresponding phi will be exactly symplectic. And therefore, what we will do is we will actually use a neural network to parameterize S. And then we train this neural network to match the training data, the time series. And then we never have to worry about symplecticity. The resulting network automatically produces symplectic maps. And because we are using this map-based approach and we have exact symplecticity under reasonable assumptions and some heavy machinery from KAM theory, you can actually prove that the long-time prediction error is going to be linearly growing with the prediction time. And this should be contrasted with that of traditional approaches for which the long-time prediction error can actually grow exponentially. So, therefore, our approach has actually superior performance because of the conserved structure. So here's one example in which we predict the orbit of a planet. So for the sake of time, let me just say that our method basically has errors that are at the very bottom, and when compared to some of the very popular and in fact landmark methods. And here is another example. This is on predicting chaotic dynamics. And in fact, the system is no longer even continuous in time. So this is something called standard map. Basically, our approach gives the best approximation of standard map. So I think I should just stop here. And I thank you for your attention and feedback.
All right, thank you very much. Thank you. Any questions?
So there is a question in the chat, which is about, is it possible to control the escape of larger local minimum by artificially controlling or forcing the system? Yes, that's actually possible. But we have to be a little more precise. So there are various ways. If you inject energy, you can escape from minimum, but then you have to remove those energy eventually. And you can inject a noise. So you have all sorts of methods to do so. But of course, the problem is to do so in a way that that is robust. So if one wants theoretical guarantee for non-convex problems, that's usually very, very difficult. But I think this is an excellent question. Thank you.
Other questions?
Hello, Prof. Tao, I have a question.
Yeah, please.
Okay, so just now I see your solution that you use generating functions to attain symplecticity, right? So
Yes.
I'm just thinking that how did you do the error bound? Is it just naturally follow from the KM theory or the mathematics theory, or?
Yeah. Thank you for the expert question. So so in fact, we basically revamped KM theory. So KM theory is basically a theory based on, let's say, Birkhoff normal form for maps. So we basically invented an analogous theory that is based on generating functions. So here the map is actually generated by the generating function. But you can actually do something similar. I'm not sure if I provided enough details.
Okay, so somehow you modify the KM theory for this particular purpose, right? Is it what you're saying, or?
Yeah, that's what I'm saying. So so KM theory is brilliant. What we did was not brilliant. It's based on using the components of KM theory and reconstruct everything together for maps that are not explicitly defined, but implicitly defined by generating functions. It's still very technical, and if some reader doesn't understand KM theory, it will not be easily understood. But I think I want to give the credits to KM, not ourselves.
Okay, thank you very much for sharing.
I have questions
please.
about the large learning rate.
Yes.
So I was wondering, have you considered like running rate schedule? So because sometimes people use like cyclic learning rates, so then you can consider situations where the learning rate is dynamical itself.
Yeah, that's a great question. So so we are actually investigating this. So in addition to large learning rate effects that I talked about, there can be additional effects because the periodicity of the cyclic learning rates schedule can actually create resonance with the internal dynamics. So that's actually something that we consider to be very interesting, but we don't have results published yet. So if this is something you want to explore together, I'll be very happy to chat more.
Yeah, because it's very I'm just very curious about this because your results show that large learning rate leads to flat minima. So then it would be really nice to see what happens if we use different schedule for the learning rate? So maybe make it cyclic or make it large at the beginning and then slowly decrease it. What will happen to the flatness or the minima that you found, right?
Yeah, I agree. I completely agree. So it depends on the scales. It depends on the scale of the periodicity of your learning rate. It depends on the scale of the fluctuation of your learning rate. And it also depends on, for example, if you have decay, how these time scales actually interact with the scales of the dynamics of gradient descent. So yeah, so I agree with you. It's all these things are very interesting to look at.
Yeah, definitely. Thank you for the talk. Very nice.
Thank you.
Hello, Dr. Tao. I have a question.
Yeah, please.
Yeah, last few slides you talk about the symplectic map. Is that
yes.
from the variable PQ to capital PQ, you have
That's
a map phi.
Yes.
That phi is a symplectic map, yes or no?
It is symplectic.
It is a symplectic. That means this keep the symplectic structure, right?
So okay, so let me explain. So there are two things.
Right.
There are two things.
Yes, right here.
Okay.
There's a PI, QI, something like that.
Yes. Yeah. So I assume that the truth is generated by a symplectic map. So it maps QI PI to QI plus 1 PI plus 1. And now I want to find this map. If I use a black box function approximator, I can get an approximation of phi, but it'll no longer be symplectic. What we did is we found a way to construct exactly symplectic function approximator. So that's what we learn. What we learn from the data. It's an approximation of phi in the sense that it's not exactly phi. You still have function approximation error of a neural network, but nevertheless, you have no error in symplecticity. What you have learned is going to be exactly symplectic. And this helps us obtain better long-time accuracy of the prediction.
But my question is, you didn't check the phi is keeping the symplectic structure, not yet, right?
No, so if the underlying, if the data is, for example, generated by a Hamiltonian dynamics, then that's going to be symplectic. That's an assumption.
Oh, that's your assumption. Yeah, this is something different. I'm doing integrable system, in particular for those Hamiltonian structure using symplectic form. So maybe you can find some conservation laws there using the symplectic structure.
Yeah. Okay. I agree. I agree. Yeah. So,
okay. Thank you.
So no, thank you. So the field is very active actually. So people do all sorts of things. Learning conserved quantities.
Conservation laws. Yeah.
Learning. So here we are just assuming that the data is generated by a symplectic map. So
you assume you're already
the data
there,
comes from.
Okay.
The data comes from a mechanical system, and we want to have a faithful approximation of the mechanical system.
Makes sense. Yeah, discrete simplex structure, so there's something very difficult to find the conservation laws. Yeah, I know that. Yeah.
Oh yeah. Okay. I agree.
Yeah.
I agree. Well, so there is a discrete Noether theorem. So the problem is that given a discrete map, there is not always an associated discrete variational principle. But if there is a discrete variational principle, then you have conservation laws. So if you want to talk more, I'll be happy to send references, etc. So this is known.
Okay, sounds good. I'm gonna send you email regarding the further discussion. Thank you so much.
Thank you.
Yeah. So I think there are 2 questions on the chat.
Yeah, thanks. So the question is about the difference between learning the Hamiltonian function and learning the symplectic map. So this is a great question. So the answer is a little detailed. So number 1, learning the Hamiltonian function is not enough, because then you have to numerically integrate it using a symplectic integrator in order to get a symplectic map. So that was done. So in the beginning, there was HNN, which just learns the Hamiltonian function. So it's better than just learning the vector field, because somehow it gives you a little bit of structure, attention to the structure. But then the integration is done by forward Euler, and then the structure is lost. And then there comes other stuff like SRN, and then other modifications that merge numerical symplectic integration with HNN, and then the results become a little better, etc. But still, so number 1, you still have to you have to carefully deal with the 3 sources of error. Sometimes you can eliminate one. Our paper has a detailed discussion, but you still have more error here. And as a consequence, so if you take a look at this plot, so we have HNN, which is like this guy, and we have SRN, and then there are newer stuff as well. So SympNet approximates actually symplectic maps in some sense, but there are additional reasons that make it still to be not as good as what we have. But yeah, so all these are actually fantastic methods. It's just things keep on being developed. So symplectic map is not just a discrete generalization of Hamiltonian dynamics. So standard map is a symplectic map, but it's not a Hamiltonian system. You cannot find a continuous counterpart. So what the context that we considered is a little more general. Sorry, I was very fast and high level, but I hope I answered a little bit. It's not only just a numerical integration, because so that plays a role, but in fact, okay, so think about this. So you are just given data. So you can approximate the Hamiltonian. You can say, okay, so this f is generated by a Hamiltonian, but how do you get the time derivative? So you have both, numerical differentiation error and numerical integration error. And in addition, you have function approximation. So so yes, it's correct. Numerical integration creates complications, but the other things also create additional complications.
All right, thank you. Any other questions? Okay, it seems not. Yeah, okay. Thank you again, Molei, for the very nice talk. And then we probably should talk again about this because we are working on something similar. Yeah.
Okay, looking forward to it.
Yeah, thank you very much. Thank you. Take care. Bye-bye.
Thank you.
Bye.
Thank you.